Hi, my name is Eugene Tan, and this is visualizing the structure of network traffic features across the IP address space. As a brief introduction, online network traffic is observed every day, as online network usage has skyrocketed in the past 2 decades due to the increased use of technology within everyday lifestyles. As a result, we can see that network traffic can often be used in both benign and malicious methods, and as a result, understanding the behavior and the structural characteristics of network traffic is of great interest due to how often and how increased network traffic is and how involved it is with everyday life. As a result, the IP address space of the internet is an interesting space and an extremely large space, and therefore characterizing the structure of this space is inherently difficult. This combined with network traffic, we're able to see how network traffic exists on the IP address space. Examining the structure of network traffic and its behaviors based upon key characteristics associated with each network trace can offer valuable insights into the IP address space by offering indicators of how its features can form relationships with other features, see the relationship between feature values and whether or not a IP address or host address is malicious or not. But also, most importantly, we're able to see the distribution of network traffic across the entire IP address space through visualization. As a result, how can we best study the structure of network traffic and its corresponding features across the IP address space? This question is the primary question that drives this work, and as a result, we can go into the background which introduces this idea. For the primary core method of this approach, we utilize something called a Hilbert curve, which is a multifractal structure that maps one-dimensional sets of data to two-dimensional spaces. This is extremely useful in this context because when we're handling IP addresses exist as numbers. And so being able to map numbers to a two-dimensional space, we're able to then see how each number corresponds to a specific pixel coordinate, allowing us to see exactly how multiple IP addresses compose a structure or a specific shape on the ultimate 2D representation. To accompany this idea, we use color theory and colors to balance this approach by providing visual indicators of whether or not a given feature or a given attribute is of a larger value or a smaller value. And so how this is handled is by using both the hue, saturation, and lightness values that are the values that compose every single regular shade of color that we see today. So hue, saturation, and lightness values directly impact the RGB value they become mapped to, because hue is directly associated with the color that you see, and saturation is directly associated with how dense or how strong the color appears. And so you can see that in this image, the saturation at very low levels is identical, and that's because when all colors become desaturated, they all go towards the same hue, saturation, and lightness value. And so we're able to see how that interacts on the visual, and we apply these hue, saturation, and lightness values within this work as methods of visualizing and offering a better approach or better visual to understanding the image itself. So we also notice that feature values within this work are also known as aggregated attributes that are observed within the network traffic itself. And so these feature values are just indicators or characteristics of the network traffic that we're observing or the network trace that we're looking at. Identifying relationship patterns or unique behaviors between these features using visualization provides insight to the structure of network traffic features because it lets us see whether or not there's an intersection between specific features or whether there's a relationship that directly correlates to specific behaviors that we may see in network traces itself. So as a result, generating visualizations using color and the Hilbert curve offer valuable image references to behaviors that we may observe within network traces by specific host addresses. So the primary method we take to approach solving this problem and this question is by using a Hilbert curve to map IP addresses to a corresponding XY position within the curve grid. This is done with the Hilbert curve because Hilbert curves have a specific property of data locality. Therefore, IP addresses that have a numerical value that are very similar in numerical value. So IP addresses that are in the same subnet or similar prefix will be mapped to a closer location. So as a result, the Hilbert curve preserves data locality, which is a unique property that we utilize here to visualize the entire IP address space. Another keynote, as mentioned before, is majority of the hosts in IP address spaces are benign host addresses which exhibit non-malicious traffic and have generally normal feature values. However, we are also able to notice that specific host addresses may be malicious hosts, which can exhibit higher levels of attack traffic or contain more unique and distinct features. And these unique and distinct features can then ultimately be found visually based upon the corresponding color scheme and color values that they're prescribed due to how they appear. As a result, to examine the structure of the IP address space, we visualize IP addresses by using two feature values mapped to saturation and hue. The saturation and hue values are then each going to be computed based upon each specific feature. Therefore, each feature controls one dimension of the two-dimensional space in terms of coloring. The saturation and hue value is then determined the pixel RGB color, and that color ultimately distinguishes the relationship between a given feature and another feature. This is directly shown in the legend below, where we can see that density and the feature of the minimum interpacket gap is going to be a two-dimensional space where density is increasing, the saturation increases, and with the min IPG increasing, it becomes increasingly differing in hue color. So you have an upper bound and a lower bound of the hue color. We examine the effects of network traffic anonymization within this context of resulting network traffic by comparing the resulting visualization of both anonymized and non-anonymized network traces. To anonymize network traces within this specific case study, we leverage the DAG scrubber tool from the USC ISI ANT project, which uses an anonymization program called CryptoPan to produce an anonymized PCAP file. And so using both the regular and anonymized PCAP file, we can then derive and compute feature values for both anonymized and non-anonymized files, and then use both of these corresponding files for visualization. So in this particular example, using two feature values, one value being address density and another being minimum IPG for this specific example, we can map each feature CSV file onto the curve, resulting in two contrasting images at various depths. So for this specific example, we examined the prefix lengths of /12, and it is exampled below. So here we can see that within these two images, the anonymized PCAP image is the one above and the regular PCAP image is the one below. From the image itself, we can determine that within the regular PCAP image, we are able to tell that the color is far less diffused, and a lot of the concentration of very saturated colors don't diffuse out to the squares around it. However, we see that in the anonymized PCAP file of the exact same file, originating file, we notice that the original areas that were highly saturated diffuse outwards significantly. And so we're able to see that in the anonymized PCAP, we're witnessing a larger degree of saturation across all areas on the IP address space. As a result, we notice that anonymization of network traffic traces directly affects the resulting visualization. Network traces which contain no anonymization compared to anonymized files, like using the DAG scrubber tool, have denser concentrations of color and are not as diffused. And so we're able to see that the anonymized PCAP file tends to increase the saturation and also generate a larger diffusion of color outwards. And so ultimately we can see that the structure of network traffic features changes drastically by anonymizing network traces. And the structure here, which is visualized, is only an instance of a single structure, and the image will also change accordingly based upon other features to be examined. And that is the current project status as it is. Thank you.